Hello, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning, and we are at the topic optimization techniques, which is topic number 6 in the list of topics. And this topic consists of various concepts in the form of questions and answers, which are divided into subsections. So we are looking at the video number 6A or lecture number 6A, and this video lecture uses the Easy MCQ personalized learning management system available at www.easymcq.com/GoGet. So we have adopted the approach of content delivery, and this is not like the conventional approach which has been being used using slides, and it has numerous advantages, and some of those advantages are written in front of you in the slide. So please take a look at it and you will know the benefits. And this learning management system, which I mentioned, the address is given in the green color URL. And the usage of this personalized learning management system is explained using 6 videos. And the location of those videos is given in blue color. So, what are those advantages? It provides very powerful full text and basic text search, which are not there in leading LMS, and it also provides the end user with having any vision limitations to customize the interface. And furthermore, all the content is kind of available in a hierarchy in a drop down menus, which supports working and learning on a smart device with limited screen. Then it tracks your progress, so you know what you have done, what you need to do. And then of course there are online exams with online grading and averaging the results and letting you know what is your level of understanding. So we have used the approach of question and answer, which is more engaging, which is more proactive, and which promotes thinking. And of course, we have also used the traditional learning approach, where details are provided. So this is a blended learning mechanism, which is the best of both worlds. And these are the topics which are covered. And we are at topic number 6, which is the optimization techniques. And the details of this topic is in front of you. So we have these blocks of color which identify which concepts Q&A are covered in which topic. Say for example, lecture 6A shown in yellow covers the first 3 Q&A or the concept. Similarly, in green color is the next 3 Q&A, which is 6B and so on. So without further ado, we move on to the actual course and start from there. So we start with section 6A, optimization techniques. So what is the objective of optimization in deep learning? So that's the concept we will be exploring. So this is at a highest level, the objective of optimization being to minimize the loss. Okay. And then when the loss is minimized, then there is an improvement in learning. How that improvement is there, that we will discuss. And it enables generalization. Generalization is the key to machine learning. Okay, generalization means that able to, say for example, classify unseen images, say for example in the case of images of dogs and cats, or maybe able to differentiate for the unseen. So if we look at more detail here in this is the diagram. So we have the loss and we have the weight. Okay, and this is the kind of the search space 2D representation. So this is the global optimum, or the where the loss is minimum, and this is the local optima, where the loss is of course less as compared to this peak and this peak, but that is not the global optimum. And this is the log of the likelihood function, right? So our objective is to reach this point. So this is a two-dimensional representation. This is more complex. This is a three-dimensional representation, right? So we have this is the global minimum and this is the local minimum, all right? And this is the saddle point. What is the saddle point? We have already discussed. This is the saddle point. So at this point we have the gradient almost zero, and in the neighborhood the gradient is also zero, but as we move around there is a decline in the gradient, right? So the objective is to reach this global minimum. So this is the three-dimensional representation. So we want to minimize the loss and we want to improve the learning. So what we will be covering are these details. Okay. So in a nutshell, the objective of optimization in deep learning is to find the best set of parameters, the best set of weights, and the best set of biases. That we've already covered. What are the base biases and what are the weights in when we discuss neural nets. That minimizes the loss function. That is the objective. Because when the loss function is minimized, okay, that translates into the difference between the model's predictions and the actual targets. Okay, so for example, hundreds and thousands of images, and we show an image which was not seen before, and our model is able to identify that what are the emotions on that person's face. So we have the optimization techniques, and what do? They adjust the parameters, and these parameters are adjusted iteratively. Okay, and what is the purpose? The purpose is to reduce the loss, thereby enabling the model to make more accurate prediction. So if we get more precise to minimize the loss, that is the objective. And so the optimization reduces the model's error. How? By minimizing a loss function. Okay, and that loss function can be highly nonlinear. So when this minimization takes place, this directs how the model adjusts its parameters while the training is done. Why? To improve the prediction accuracy. That's one thing. Then improve learning. That is the objective of optimization. So what the optimization does is drives how neural networks learn from data by updating the model weights effectively. So when it is done, it is ensured that the models converge efficiently and they adapt to complex tasks. Okay, so that's the second objective. So what is the third objective? It is enable generalization. So what it means, good optimization ensures the the model performs well on the unseen data. Unseen data means the data on which the model was not trained before. So this prevents overfitting and underfitting. So that helps the model generalize beyond the training set, right? So here it is. So if you are interested, you should be reading. So I can reduce this, and if you click on view description answer number 1, so these are all the details which I just shared with you, discussed with you. And if you're interested, here are the references. So a lot of material is available here. So we now move on to the next Q&A, and that is, what are the deep learning optimization challenges and their mitigation? So what are the challenges? Okay, let's look at this. So we have these challenges, right? And I will go through all of those challenges. So basically, deep learning optimization is critical, is a critical aspect of training neural networks. And of course, it involves minimizing the loss function. Why? To find the optimal set of parameters that we have discussed before. However, this is a very tough task, and it is fraught with challenges, okay, that can make optimization difficult, and it impacts the model's performance. So this is what AI engineers do. So here are some of the key challenges. These are some of the key challenges, okay, in deep learning optimization. Now this basically, what basically is showing this diagram, that is one of the challenge, okay. So we have here something called as the convex functions. So in convex functions, if we connect any 2 points on the surface, so to say, these points, that the line which is drawn, that line remains within this convex 2D, 3D volume. But this is not convex, this is concave, right? So if we connect 2 points, they basically they do not remain there. Okay, so this part is kind of convex, right? But with reference to these 2 points, they are not convex. All right, they are not convex. So this is a non-convex function, right? This is more challenging. This is not that challenging because there is a single global minima, the single global minima, right? So gradient descent can take us to this point, but here it's a different story. There is minima over here, There is a minimum over here. There's a minimum over here also. There's another one. And based upon the shade of the color, this seems to be the global minima. So if you are here, it's very challenging to cover this peak and then come here, and then it's very, very challenging. Okay, very difficult. So we have these challenges. So what are these challenges? For example, vanishing and exploding gradients. Vanishing and exploding gradients. Okay. So gradients can become extremely small or large during the back propagation. So what it translates into making weight updates ineffective or unstable. So this ineffectiveness or instability that kind of hampers the training, especially in very deep architectures. Deep architecture, there are many layers of neurons like RNNs. So what would be the consequence? It leads to slow convergence or divergence. Okay. Then is local minima and saddle points. So optimization landscapes which we come across in deep learning, which I am showing you here also, okay, they contain many local minima and saddle points, right? So local minima may not be too problematic, right? But saddle points with zero gradients in multiple directions. So this is a multi-dimensional space. So over here I'm just showing you 3D space. So that can trap the optimizer and slow down the learning significantly. Trap means that it can the optimizer kind of gets stuck. Then is the poor conditioning of the lost surface. Poor conditioning of the lost surface. Now try to understand when the lost surface has steep slopes. Steep slopes mean that the gradient is very high in not in all directions but in some directions, and flat areas in others. So nearly zero gradient. So it is called, which is poorly conditioned. What is the consequence? This leads to inefficient updates and again slow convergence. So slow convergence means that the iterations will be more, and when the iterations are more, the processing time is consumed more, the energy is consumed more. So what we need to do, careful tuning of the optimizers and the learning rates, right? So as to efficiently navigate that surface. Okay, that you can, this surface we are talking about. So overfitting. All right. So deep models, as which is I'm showing you the non-convex, and this is a simplistic because it's only showing for 3 dimensions. There can be multiple dimensions with many parameters, like many dimensions can memorize training data. So when memorization takes place, the generalization is compromised. So instead of learning the general patterns, is memorizes. Now memorization results in overfitting, and and the consequence of overfitting is that the performance of the model is reduced or it is inefficient for unseen data. So what will be the result? Making regularization, early stopping, and proper data augmentation essential, which we have discussed in topic number 5. So we have to go through all of this for effective optimization. So it means that the scope and the complexity of the problem increasing, so is the requirement of processing power. Then the large scale and high dimensional data. So when we have big data, training on say massive data sets, and of course not only in volume but in dimension, high dimensional inputs. So as a consequence, the computation time and memory requirements will increase, and optimization will become more challenging. So there will be requirement of techniques like mini batch training, parallel processing to take care of the processing power, and there would be requirement of specialized hardware also for efficiency, like with GPUs and TPUs. So that translates into cost, and that translates into money, and that translates into energy also. Now what is meant by learning rate scheduling? So let me, okay, I'm sorry about that. So let me let me show you more details. Okay. So we were at learning rate scheduling. Learning rate scheduling. So learning rate scheduling. Now, if the learning rate is fixed, that can cause instability or slow convergence, very slowly, small steps. And scheduling strategies like step decay or cosine annealing or warm restarts. Basically, what it does, it adjusts the learning rate dynamically. Okay, so which helps the optimizer convert faster and avoid poor local solutions. Because if the learning rate is high, it can skip or it can miss the local minima. I'm sorry, the global minima. And if it's very slow, it's slow convergence, so it has to be dynamic. All right. So then is the non-convexity of the loss function, which I have shown you here. So now in real life, the deep learning functions are typically non-convex. They contain many valleys, many peaks, as you can see in this diagram which I've shown you. And this makes it hard to guarantee global convergence. There is no guarantee. And optimization algorithms must navigate complex net and landscapes to find the acceptable minimum. So we have like kind of compromised and we are saying acceptable minimum, not the global minimum. So you see, this is a non-convex loss function. Okay. So the acceptable is this is okay or this is better. So the next concept is why do modern optimizers still work despite the non-convexity of the loss function? So in the previous Q&A, I showed you a non-convex loss function in a 3D environment. So what are the reasons for it? I'll explain it to you. First of all, uh, despite the non-convex nature of deep learning loss functions, okay, modern optimizers like stochastic gradient descent, SGD, Adam, and R, and others, they are remarkably effective in practice. Now, why they are successful? There are several underlying phenomena, okay, that help them navigate the complex optimization landscape. This is the landscape we are talking about, okay, especially when we are talking of deep neural networks. Because unlike the convex problems, non-convex problems include many valleys. Okay, there are many valleys as you can see here. There are many valleys, ridges, and flat regions, which of course theoretically make optimization difficult. However, the real world neural networks exhibit characteristics that somehow mitigate these challenges. So this the purpose of this lecture and is to like look at them. So these are the more details. Okay, so we have non-convex loss surfaces and of course robust optimizers. So the reason being that let's discuss what we are. Okay, so non-convexity is less problematic in high dimensions. Why? Because many local minima yield similar performance. So therefore the optimizer is more likely to find a good solution. We are not saying the best solution, a good solution even without global convergence, because the cost of getting the optimal solution is very high. Then is the robustness of the optimizers. Modern algorithms are built to handle gradient noise also, curvature, and saddle points. So these adaptive features of the modern algorithms, they help navigate complex loss surfaces like the one which are in front of you. Okay, and their adaptive features help navigate complex loss surfaces. Okay, why? And these are the surfaces where the basic optimizers struggle. Okay, that's another reason. Then good local minima. So deep networks with their valleys and ridges, they contain many local minima with comparable training and generalization error. So finding any one of these good local minima, not the best one, okay, is sufficient. So that reduces the reliance on finding the absolute global minima, which is very expensive. Okay. So although this is the poor local minima, right, and there are good ones because they are very very deep, right, but the modern optimizers, they are able to work. So these are the details. So we are looking at good enough solution, and you can go through those details, and here are the references also. Okay.